how do we tie the mathematics, the equations, to what I just said, to all these physical interpretations, these physical objects, these mediators that Mother Nature, Father Universe, right, whoever you believe in, use, right, every day to do their simple work like gravity and light and so on, magnetism. How do we tie equations to them? So now let's look at the equations, okay? And we start with this, okay? Again, let's go slowly. I'm going to try to go slowly today because not everybody understands math. If you had high school math, you'll probably be able to get through the lesson today, the lecture. And I'm going to try to go slowly so that you understand every bit that's happening, okay? So here's the first one, and that's where we started earlier, and that is that we're going to replace the electromagnetic wave with the electromagnetic rope. It's a rope, it's a thing, okay? Not a concept like the wave is, okay? It's not made of, fields and vectors. It's made of threads, and so it's different. And some people can't tell the difference. People say, oh, just gave new names to the fields. No. The field is a concept. A value at each point in space. That's what the word field means. That's not what we're talking about. We're talking about threads, physical threads. This is a rope, and it's made of threads, okay? So that's important to understand. We're talking about objects here, things, okay? Things that go through things, because the ropes go right through the ropes, just like neutrinos go right through neutrinos and through other matter. Okay, so that's the starting point, and here, we already really touched upon the first equation because, see, the the theory of everything, kind of like the grand unified theory which united all the forces according to quantum, the theory of everything tries to unite gravity with electromagnetism primarily, right? And so we need the equations. We need to see how these equations tie into this. And here you have it. C equals frequency times wavelength. That's our first equation. And we're going to use that equation. We're going to put it in the grand equation that is actually the grand unified theory, or the theory of everything, if you prefer, right? And it's essentially the same. They've been looking for a single equation. And that's what we're going to talk about today. Okay, so there you have it. C equals frequency times wavelength. What are we saying? We're saying that C is equal to number of links times the width or the length of what we call the length of the link, okay? And you can see why a rope is the one that can only do that. It's the only thing imaginable that can imitate that equation, because, the less torque that a rope is, the longer the links are and the fewer links you get. And the more you torque it, right, the shorter the links and the more links you have. That's what that equation says. The only thing that can model that equation is a rope. There's no other option. Even a chain can't do it, because each link is separate in a chain, right? It's got to be a thread that goes all the way. It can't be just links that are united, for like a chain. Okay, so there you have your first equation. That's the equation we're going to later on put in the other one. Okay, so there's the first step. Okay, that's the one for light. I think it's straightforward. Okay, what's the other equation? Well, here we have it. And it's not mine, by the way. None of these equations are mine. Okay, I just want to make sure. And that's Newton's equation, gravitational equation. And it's they put the word force there. Okay, and I'm going to qualify that in a minute. But the equation, the traditional equation, is force equals the gravitational constant g, mass divided by radius squared. Now, as you can see, radius to the -2, some people don't like that notation. It's kind of tricky. They're not used to it. And so I do try to change that. But first, let me do something here. We're going to replace that radius and put distance. Okay, it's not radius, it's distance. And one of the reasons for that is you have oblate objects like, maybe the moon, Earth. They're not perfect spheres, so you can't really talk about radius. You have to look at distance, okay? So distance is a better word than radius. I discourage the use of radius. But distance to the -2, not everybody understands that, so I like to put it in a different format that maybe high schoolers are more used to, and it's this one. It's mass divided by distance squared, distance at the bottom. Now we can all more or less understand it. If you had high school algebra or whatever, math, right, you'll probably relate to that. Okay, but the big one here is that gravitational constant G. What does that mean? What is that G? And, nobody knows out there. Nobody in mathematics, right? And so we're going to talk about especially that gravitational constant G. And it's equal to this number, this totally crazy number that you see there. What in the world is that, right? Okay, and so people don't understand. They look at it and they say, well, every time we put newtons, the N there, right? Meter squared kilogram to -2, it was on the denominator. With that value there, 6.67, right? When we put that number, it works. So it's like tautology. Yeah, we put that number because it works, okay? But nobody has any idea what all that means. And that's all they needed really to figure out, as far as we're concerned here, to understand the theory of everything, or grand unified theory. I like to use grand unified theory because it kind of is a better notion in my mind than theory of everything. But yeah, it's it's the unification of gravity and light. How do we unite this with light? That's what we're trying to do here. How do you explain that, right? Okay, so let's get rid of this one. Let's find out what that Newton thingy is. And here it is, okay? Here we have gravitational constant G is equal to a Newton. What's a Newton? Newton is a force that accelerates a mass of 1 kilogram at 1 meter per second squared. Whatever that means to you. Okay, but there's the value. 1 kilogram meter second to the -1. Second's going to be in the denominator. And what we're going to do with this, we're going to, again, put it in high school language so that more people can probably relate to it. So, first we're going to put it in the gravitational equation, right? Because that's what a Newton is. And now we're going to simplify this a little bit so that you can understand the notation that I put in there. Okay, that's what it means. It means little g, right, is equal to 667. Also shorten that. We don't need the 43 there. Over 10 to the 11th, right? We have meter from the Newton and a kilogram from a kilogram squared in the denominator from what you see there in blue. And a kilogram meter is second to the -2. That's what you see there. You have another meter there, and second is in the denominator. The other kilogram is on the top. Okay? So hopefully you can see what I've done here. I've taken the newtons, find out what that is, put the newtons in the gravitational constant equation, and then I simplified it so that you can understand it in maybe in the high school notation rather than in college notation, okay? I think a lot of people can relate to it better that way. I mean, if you're a little rusty on math, it might take a little while for you to pick up on it again, but hopefully this is straightforward. Gravitational constant G is equal to meter squared, kilogram over second squared, kilogram squared, and we got that from the newtons, which was part of the gravitational constant G. Okay, so far so good. I hope no one's lost. Okay, we're going slowly here. Sorry, some people might be yawning, but I got to go slow for the people who are not as familiar with this equation. That's what we're trying to do here. We want to explain how this relates to the unification of light with gravity. Okay, so what are we going to do next? Well, we're going to take that meter, the meter squared, and we're going to unite it with the other meter there. We're going to, let me do this here, what I call meter cube, right? So we're going to put this meter squared in meter, right? And that becomes meter cube. So I've just simplified there a little bit so that you can see that we united those two meters. That's all I did. Some people might say, well, you can do another simplification here, and that is you have kilogram over kilogram squared. We can scratch out, right? Let's see if we can do that here, show it. We can scratch out those 1 kilogram with kilogram squared, right? We're not going to do that. we're not going to do that because we're going to lose information that we absolutely need. We need those 2 kilograms there. They were there, we're going to leave them there, okay? So no, we're going to remove the simplification. In fact, we're going to be unsimplifying the equation as we go along, because unsimplifying the equation allows us to visualize how gravity relates to light, okay? That's what we're going to be doing here, okay? Okay, so there we have it. Let's take this out of there and begin anew. This is where we ended up with. We ended up with this, okay? Force equals to that strange number there. They're strange units. Mass over distance squared. What we did is put the gravitational constant G, which is the segment that is in blue, the factor there that is in blue. Okay, we're going to try to analyze that. What does that mean? What does the mass over distance squared? You have 2 objects separated by distance. That's how simple it is. No biggie. A child 5 years old can understand what's in yellow there. The problem is understanding the blue part. Okay, that's what we're going to do next. Okay. And so what do we do? Well, the first thing we got to do is replace that word force, okay? What we're looking at is weight, okay? That's what we're looking at. And you're saying, wait, why wait? Why wait? Why wait for weight? Why do we wait for weight? Or why do we replace force with weight? Well, because what you're looking at is that equation tells you how much you weigh or how much an object weighs around the earth, for example. This is just an example, as it falls to earth. Okay, so at different levels, right, it's going to have different weights. Again, weight is location specific. You do not need to move. You do not need to accelerate. Weight is location specific. For any location around the earth, you have weight. Whether you weigh yourself or not, you already have weight. There's different weights at different distances from the center of the earth, or center of mass of the earth, okay? Okay, so if weight is a static concept, then we have to replace that not with force, but we have to replace it with tension, okay? Weight is not a force, weight is a tension. Tension is not a force because no one wins the tug of war. And a lot of people have never realized that, but tension is not the same thing as force. Tension is not a type of force. What they're talking about is when you pull a string and they say, well, measure the tension. Here we're not measuring anything. We're going with definitions. Tension means that no one wins the tug of war. Therefore, it's not a force of any kind, either push or pull. Okay? Neither one is correct. Okay? Tension is not a force. And so we're going to replace that weight with the word tension, meaning that we can synthesize this in a single frame of the universal movie, okay? So if we had God's movie there, you know, and it's rolling, all the atoms moving from one location to another, what we're going to say is that tension is, I can illustrate tension in a single frame. I cannot do that with force. Okay, for force, I need at least 2 frames of the universal movie. For weight, I can synthesize that in a single frame, and I can synthesize tension in a single frame because nothing is moving. Okay, so it's important to understand that concept. Okay, so here you have what is force. Force, an influence that can cause an object to change its velocity. And tension does not change anything. Tension means the game is tied. No one wins the tug of war, okay? Whether push or pull, by the way. Okay, and that's why we use this notion known as the little tool that I created, known as the universal movie. And a single frame in the universal movie, right? If you take a snapshot of the universe, God's camera, all you see is every atom in the universe, wherever they are in a given location. So you took a snapshot of the universe. You're outside the universe somehow, next to God, right? Or Father Universe, Mother Nature, whoever you want to say, believe in, right? The devil, maybe. You take a snapshot of the universe. What you will see is every atom in the universe at a distance from all others. That's our universe. That's how simple our universe is. Of course, you have to unite them because, as we said earlier, Mr. Muller from Berkeley University says that every atom is connected to every other atom. And if they're connected, there had better be a physical object between them, a physical mediator, physical agent, right? For otherwise, you're doing action at a distance, which is the scientific term for black magic, for witchcraft, voodoo physics. So no, you can't do physics without objects. You need objects, and if every atom on Earth is pulling on every atom of you, then there had better be a mediator that you cannot see or touch, and that goes right through another one of those mediators. Okay, so we have here the universal movie. What's the problem with what we just said concerning weight? Well, here we have acceleration. Acceleration is a dynamic concept. You can't have acceleration in a single frame, okay? You can have velocity in a single frame because it's the derivative of acceleration, but even velocity requires the notion, the definition of velocity is motion. So you need two frames of the universal movie. So that's why motion is at the bottom, right? Because it is a dynamic concept. You need at least two frames as shown by the little gray area there, right? You need two frames at least. Whereas for the static concepts such as object, distance, location, existence, all you need is one. You don't need two frames. There's no motion involved in the definitions of those words. Okay, and so where do we put weight? Well, weight, hopefully we put it at the top there. Okay, weight is a static concept. You have weight anywhere around the Earth, right? If you're an astronaut falling on Earth, and we took a snapshot at a given point in time, we should be able to illustrate weight. How do we illustrate weight under the rope model? Well, all the ropes converging upon an atom. The farther an atom is, the ropes come together. The closer an atom is, the ropes fan out. And that's the acceleration of gravity. You need several frames to see that acceleration. But for weight, single frame. Okay? So here we have an astronaut, right? And he's falling to Earth. And he's got weight at different locations. Okay? So maybe far away, he's got 25 kilograms, right? And close by, he's got 50. And so what we're saying here is that, yeah, all those atoms of his body are bound, are connected, physically connected to every atom on Earth. Okay? As he approaches, the ropes fan out. Okay? That's what we're arguing here. That's the theory, right, that we propose here. And so here we have, so we're going to replace weight with tension, and here it is, okay? Tension is equal to that strange number there, strange unit. The number's not so strange, but the units certainly are, the blue ones. We're interested in the blue ones here, right? Okay, so again, let's erase the board and start with that tension again. Let's put it up there. Here it is on the board, okay? That's what we have. That's our starting point now. Hopefully everybody has followed so far. I'm trying to go as slowly as possible so that people can more or less understand, people who've gone to high school at least and taken some math, some rudimentary math can follow through. Okay, so what are we going to do with all this? You have that there, and how are we going to make sense of it? Well, we're going to multiply all that times 1. Am I allowed to do that in math? Well, even if I'm not, I'm going to do it anyways. Okay, so let me multiply that whole thing by 1. Am I allowed to do that? 1 times all that? Am I okay there, or am I violating some law of mathematics? Well, I'm going to do it anyway. I'm going to try to get away with it. I'm going to multiply it times 1, okay? And just to make sure, that I can do this, right, let me replace that 1 with another form of the 1. Hopefully you'll allow me to do this as well. I put 10 to the 16 over 10 to the 16. Am I allowed to do that in math? I mean, 10 to the 16 over 10 to the 16 is what? 1 times all that should be that. And so I think I'm legal, right? I hope I'm legal. I hope I'm allowed to get away with all this stuff, right? Correct me if I'm wrong, okay? Send the mathematicians over to correct me. Okay, so here we have it, okay? And now you can see what's happening here. We have 10 to the 16, and I'm going to put that 10 to the 16 with a 10 to the 11 in the denominator, okay? And essentially you add the exponents there, so we get 10 to the 27. So we have 10 to the 16 over 10 to the 27. Am I still legal? I hope I am, right? Hope I haven't committed any crime. Not yet. Okay. And so the interesting thing about this, when you do this, something magical happens. Coincidence that surprised me, when I saw it. So I hope it surprises you in the same way, okay? Let's see where we get to this. Okay, so we're going to replace now that 10 to the 16 meter cubed over second square. We're going to take that meter squared over second square and factor out the velocity, the speed of light. So now we suddenly have light in our equation, okay? Unification, grand unified theory of everything. We're getting close here. Now we're putting light in there, okay? We have 300 million meters, right? These are meters. Keep in mind, it's not kilometers. 300,000 kilometers is 300 million meters squared. And you have meter squared over second square. So that is the speed of light, okay? And so just by putting that in there, just by putting that 10 to the 16 in there, I was able to factor out the speed of light, okay? And so, yeah, there you have it. 9 E16s, which is the speed of light in a different format. And what is that? We have we have a speed of light in there, in our equation. Now, isn't that nifty that I was able to remove, to put in 10 to the 16th, fudge around, kind of play with it, right? Put it in there, and with that, I was able to put light into our equation, okay? But that's only the starting point, okay? So I'm going to take that. Keep in mind that you got 0.74 times the speed of light, right? Kilograms over kilograms squared, 10 to the 27. What in the world could all that be? And so let's put that up there. Okay, let's start over. Okay, that's what I got up there. So far I'm legal. Okay, hopefully. Okay, let me know if I'm illegal. Okay. Okay, so we have that. 0.74 speed of light, kilograms over kilograms squared. What in the world can all that mean? Well, it turns out that all I did was put 10 to the 16th, and it turns out that that is the mass of the hydrogen atom. Okay? So now we have 1.67 kilograms over 10 to the 27, and it turns out that by sheer coincidence, now this is an interesting coincidence, just by putting 10 to the 16th over 10 to the 16th, I was able to factor out the speed of light and the mass of the hydrogen atom. Now, isn't that somewhat of a coincidence? I mean, you have to hand it to that equation that's just telling you what it is, okay? Mass of the hydrogen atom, 1.67 times 10 to the 27th, okay? Plus or minus whatever. We don't care about the little details, but we have the speed of light and the mass of the hydrogen atom, okay? And so this is what we end up with. We have light and we have the atom so far. Okay? This is what we have so far. And the important thing here is this is a gravity equation, right? And we were able to put light in there, c squared in there, factor it in there. And it goes together with the H atom, okay? So I just want you to bear with me for now, okay? See if you can follow through, okay? And so here we have it. That's what it means. It means that every atom in the universe is connected to every atom in the universe, right? And it sends signals back and forth. In other words, every atom in the universe is sending torsion signals to every other atom, and every atom sends all those torsion signals right back. Okay, so that's the c squared, okay? And then the kilogram is because you're using hydrogen atoms, you could say the unit of mass in the universe. At least it's the unit of mass in the rope model, okay? That is the unit of mass. It's called the hydrogen atom. Unbreakable, can't break that atom like they said they did. No, you can't bust the hydrogen atom because you can't bust the threads, right? Can't cut the threads. And so the atom is just pumping back and forth. We never split the atom. It's impossible to split the atom. It's their interpretation that they split the atom, not that they proved it or confirmed it or anything. That is their physical interpretation. Now, it turns out that, when every atom in the universe is connected to all other atoms in the universe, you have this situation where you have a skater, and she's going to troll around, and she's tugging against every atom in the universe. Okay? She opens her arms. Why? Because she's pulling against every atom in the universe. Okay? That's what's happening there. That's the reason she can do this. Okay? If you were at the edge of matter that forms our universe, you can imagine all the matter that forms our universe, all the atoms, and you're right at the edge of this, right? Not like us, we're somewhere in the center or wherever, but we're not at the edge of the universe. But if you were at the edge of matter, not the edge of the universe, I hate the word universe because universe is space and matter. We're at the edge of matter. Well, you have all the matter behind you, but not in the opposite direction. There's nothing there pulling on you. Okay, so it'd be kind of hard to travel in that direction. Okay, you'd be pulled by all the matter behind you. Okay, but why does she spin? Well, it's known as Mach's principle. Okay, Mach's principle says that you're pulling against every star or against every atom in the universe. Okay, that's Mach's principle in a nutshell. Okay, so here we have the motion of two atoms bound by the electromagnetic rope. And again, this is our model, our basic model. Two atoms bound by a rope, and with this we're going to try to explain how they are, what is out there in the universe and how it works. Okay, and so that's one motion that you have. If this is all there is, remember, let's assume we remove all matter from the universe at this point, right? And all we have is these two atoms bound by a rope, right? An electromagnetic rope. Well, they can spin like this, and that would you would think, pull them out like the skater's arm, right? It pulls them outwards, and that's the direction of being parallel to gravity, okay? Because you're pulling in the direction of gravity. That's what I'm trying to illustrate here, okay? So just bear with me for a second, okay? We're going to pull into parallel to gravity, okay? And so, yeah, you would find this in the numerator in the tension equation, in the gravitational equation, right? Because they're in the direction of gravity. If you're being pulled by the Earth, if you're an astronaut falling towards the Earth, you would be in that direction, right? Parallel to gravity. That's what I'm trying to show there. However, there are a couple other motions that, if those are the only two atoms in the universe, that they can do, and not only pull outwards, they can do this as well, okay? And this is not a linear pull like you had just a second ago with all the atoms just pulling outwards, right? Because they're scrolling around each other, right? Here we're saying that, look, what you're looking at there is a twirling motion. And this twirling motion is a squared notion because you're drawing a circle. You've got a plane there, right? And it takes away from the pull of gravity, which is in the direction parallel to gravity, right? This is perpendicular really to gravity. And so, yeah, we're going to find this in the denominator. And that's what we're saying that this is happening here. You have the kilogram squared again, okay? They're rolling around, right? Orbiting kind of around themselves, right? But the issue here is that this is what we have. We have Mach's principle there. We have the perpendicular direction, and we have the parallel direction. Parallel is in line with gravity, and the perpendicular one, which is a squared function, factor, should take away from gravity. So it should be in our denominator. Okay, so that's what we're trying to represent here. And what this takes us is to Mach's principle, which is what we replace the kilogram squared at the bottom with the kilograms on the top from the H atom. Okay, so now we have Mach's principle in there. That's essentially what that equation is representing. Okay, and so again, let's start with Mach's principle. Let me get rid of this. We put this back up here. Give me a second. Where is it? Okay, so there we have it. Light times Mach's principle. And we still have something left over, which is that 0.44 meters. What in the world is that? And we're trying to figure that out. And it's got to do with light, okay? And let me show you why, because we have this. We have the universal amplitude of the wave. Remember, a rope or a wave, doesn't really matter, has three features. Has frequency, wavelength, and amplitude. Okay, aside from the fact that there's a invisible axis along which a taut rope lines up through. So we can draw through a very taut rope. You can draw a line right through the center of the rope. Okay, an axis. Okay, but the important parts there are the amplitude, the link lengths in the case of the rope, and the number of links. Those are features of a rope. Okay, so that's what we say is the 0.44 meters, because that belongs to the light portion of the equation. And here we're going to synthesize and say, look, we're going to replace the little c there by frequency times wavelength. Hopefully I'm allowed to do that, right? Because that's what the little c is. And remember, it's a constant. So this gravitational constant has to be made of constants. And we're saying we have two constants there. One is the mass of the hydrogen atom. The other one is light, okay? The frequency times wavelength. And then we have the average wave, amplitude of the wave in the universe. You say, can that be possibly true? I mean, here you're talking about, you're talking about this. You're talking about, let me get this one out of there for a second. Okay. You're talking about this. You're talking about a rope, but a very thin, you have to imagine this extremely thin, unimaginably thin rope, right? And you're saying, hold it, this thing stretches out half a meter, 0.44, half a meter? How can that possibly be? And if you say, well, if you just look at the thread, the two threads, very thin threads, you're saying, well, that's nonsense. There's no way that can possibly be half a meter wavelength. But now let's look at the whole universe. Okay, let's look at a galaxy. You have the galactic magnetic fields, right? And you have these fields that go around the whole galaxy. The galactic field encapsulates the entire galaxy. And so you have this situation where I've illustrated here. That's what a galactic field might look like. You have all the threads sweeping around the galaxy. Not only do they maintain the integrity of the galaxy, right? Because remember, a galaxy, the way it is under the rope model, is you have this, which is the explanation for dark matter, essentially. You have a galaxy, all the stars are bound to each other. That's the reason they don't go flying out of a galaxy, because they're all physically bound to each other. Every atom of a star is bound to every atom of another star, of all stars. And that's the reason, a galaxy rotates in situ like a carousel, right? Otherwise, if it were all made of particles, the stars would fly away. Okay, so galaxy is, united by all these threads and ropes that interconnect them. So that's the galaxy. The reason a galaxy sticks together also explains dark matter, because the reason that the stars on the outside fly faster or at the same speed as those on the inside is because the whole thing rotates as a carousel. Okay? And why? Because they're all physically connected. It's got nothing to do with mass being put in there or anything like that. Okay, so let's return to this one. On top of that, we're going to put the galactic field, which is something like that. You would have all the threads flowing out the top and coming through the bottom, in this case, right? And that maintains the integrity of a galaxy. So what's the issue there? Well, there you have amplitude. The wave, the rope has split apart. In other words, has opened up. And you have this situation here. Let me remove this for a second. Okay. And what you have this situation where the ropes are, the threads are swinging around the entire galaxy. Okay, so some are coming up, the others are coming down, but why? Because the amplitude was increased. And so when you factor the amplitude of all the ropes that make up a galaxy, all the threads that make up the galactic magnetic field, right? Then yes, if you, with that amplitude averaged out throughout the universe, plus all the atoms that are connected through ropes with each other, yeah, you could probably conceivably end up with a number like half a meter, 0.44. And that's what we say is that other factor in there. And of course, it's good to put it in this context that the light part is energy and the atoms part is matter. So we have these words that they like in mathematics, energy and matter. Well, there you have it. That's the energy component and the matter component of the gravitational constant G. And again, you can see light is represented by the amplitude, the frequency, and the wavelength on the light side. And on the other side, you have the matter portion, which is the hydrogen atom, a constant, okay? And Mach's principle, the fact that, it's not that the atoms are twirling around, it's that everything is pulling from every side on those atoms, from every atom in the universe. That's Mach's principle. You don't have to have motion for that either. You can represent that, in a static concept, such as the universal movie. You can represent it with ropes, just connecting one atom to every atom in the universe. If you could take a picture of that, right, you would have that atom being pulled from every side. The ones that are parallel to gravity, that's your hydrogen atom. The ones that are pulling outwards, that's the twirl, you could say, if the only things you had in the universe were two atoms bound by a rope. So that's the notion in general. Okay. Anyways, the point here is we have the equation, and it's Newton's gravitational equation. It's just not a force, it's a tension, right? It's a static concept. Weight is a static concept. That's what the equation represents. I replaced radius by distance. Why did I do that? Because it's not the distance traveled of mathematics, it's distance separation. The distance of physics, separation between two objects. That's what Newton's equation shows. There is no acceleration in Newton's equation. All we have really is a static concept, weight, and weight is a static concept. You have separation between two objects and all the ropes interconnecting them. The ropes are represented by the part of the equation that represents the speed of light plus the average amplitude of all waves in the universe, all ropes in the universe. And the other portion has the other constant, which is the mass of the hydrogen atom.